Hello, and welcome to the United States Geological Survey's public lecture series. Thank you for joining us this evening at our new start time of 6 p.m. Pacific time. We hope this will give our Central and Eastern States viewers a better opportunity to join us. My name is Mitch Adelson, and I will be your host and moderator today. Before I introduce our speaker, I just have a few announcements to make, and this will allow others out there in virtual land a few extra minutes to get logged in. First, I'd like to give you a heads up about our lecture for next month. On June 30th, we will have Michelle Coombs, scientist in charge of the Alaska Volcano Observatory, talk about keeping tabs on the volcanoes of the last frontier. So please be sure to save the date and join us next month as well. At the end of the lecture, I will provide information on how you can join our mailing list so you'll always be in the know on these upcoming lectures. And next, we want to take a few seconds to give you some tips on a few features of this Teams platform. If you are watching this from a desktop computer and need to turn on closed captioning, please look at the bottom right-hand corner of the screen for the closed caption icon. That's the one with the two little C's. Another feature we want to direct your attention to is the question and answer panel, which can be opened by clicking on the question mark icon in the upper right-hand corner of your screen. At the end of the lecture, you will have a Q&A session, and this is the panel where you can submit your questions to our speaker. Please understand, we may not have time to answer all the questions, but we will do our best and appreciate your understanding in advance. And now, it is time to begin our lecture for this evening. Tonight, we have the pleasure of welcoming Paul M. Young, Director of the USGS National Civil Application Center. For the last 5.5 years, Paul has served as Director of the USGS National Civil Application Center, which analyzes military and intelligence remote sensing data in support of USGS science missions. Paul started his career with USGS over 30 years ago as a cartographer compiling USGS topographic maps. Since then, he served as a physician overseeing systems development, information management policy, and earth and natural resource research and assessments. So without further ado, let's all give a warm virtual welcome to Paul. Paul, the floor is all yours.
Okay, Mitch, thank you very much for that introduction, and thank you to Amelia for your help as well. Mitch, just want to do a quick slide check. Can you see my title slide? Yes. Oh, okay. I got ahead and nod. Thank you. All righty. All right, let's dive in. I organized this talk or this presentation around my title. I have a rather long, wordy title, so let's break it down, and this will serve as a bit of an outline for tonight's presentation. So, first of all, I'm going to answer the question: what do I mean by sunk cost well spent within the context of this topic? And then next, I'm going to answer what is remote sensing. Now, if you have been to other USGS public lectures, you perhaps have come across remote sensing or other presentations that mentioned it, but want to make sure that everybody was up to speed on that topic. And then third, a story I really like to tell, and that is how the U.S. Geological Survey, a civilian agency, came to partner with the military and the intelligence community. And then next is how have we benefited from that partnership? And the main part of my briefing tonight is how are we using remote sensing technology from the military and intelligence community to advance USGS and other federal science missions. I'll also direct your attention. I've got two pictures of the Statue of Liberty here, and the one in the lower right, you'll see again in a couple of minutes. So just keep that image in mind because it's going to come back up. Okay, so what do we mean by sunk cost well spent? Well, investments in Earth observing technologies are important to our defense and intelligence communities, and to help them meet their purposes and important missions to keep our country safe and secure. And so both the defense and intelligence community do make investments in Earth observing technologies. Now, the well spent part comes in because civil agencies such as the USGS do benefit from those investments made by our defense and intelligence community partners. And so it helps us to reduce our costs because the investments that they are making save us from making those same investments. We also take advantage of bulk buying, and this is something that each of us can understand, right? When we go to the store and we need to buy paper towels, we know if we buy an 8-pack of paper towels, the per cost of each paper towel roll is cheaper if we buy a pack of 8 versus if we buy them in just packets of individually wrapped, right? And so we benefit from this bulk buying, and I'm going to come back to that concept in a bit as well. And so within my center, we like to say that we operate in this triple junction, or the intersection of the defense and intelligence community with federal civil agencies such as USGS. And this triple junction is really good government. And through this idea of a sunk cost well spent, we believe that we're saving the taxpayer quite a bit of money. Now, an example of this sunk cost well spent is really something that I think each of us on this lecture or listening tonight can understand. And that is that our phones, our devices that we carry around with us, we know have the ability to tell us where we are or to help give us directions if we're going from one location to the next. Well, that location information is coming from the Global Positioning System, or also called GPS. Now, the Global Positioning System is a series of satellites that have been planned, built, launched, and operated first by the United States Air Force and now by the United States Space Force. So currently, as of today, there are 30 GPS satellites in Earth orbit. Now, originally, the GPS system was designed for military navigation purposes, but now by law, it is required to also support civil purposes. So that's why each of us with a phone or a device are able to connect up and know our location or the location of that device through access to GPS. Now, truthfully, GPS touches every part of our society and economy. During the last couple of years of the COVID pandemic, many of us have benefited by at-home deliveries. Well, those delivery trucks are planning their route with GPS. So anything dealing with transportation, whether it's trains, trucks, ships, planes, all rely on GPS. First responders, when they need directions for, get to our house or a location, that call 911, and so on. So very ingrained in our society. Well, this is a sunk cost well spent. This is an investment that the Department of Defense has made, but we everyday citizens have access to that. So, okay, that is sunk cost well spent. So what is remote sensing? Sort of the classic textbook definition is it's acquiring data or information without making physical contact. And within the Earth sciences, it is a very vital tool. And I'll be spending a good part of my presentation giving examples of how we use remote sensing within the Earth sciences. So just a few examples. So if you're standing on a hill viewing a valley below, you are a remote sensing instrument. You're observing that valley below, but you're not physically in contact with the valley. And in the same way, if you're taking a photograph of a scene, that camera is your remote sensing instrument. And again, you're not physically touching or a part of that scene, but you're some distance away. So a couple of examples from the sciences. So a sonar instrument on a ship that's imaging the ocean floor is a remote sensing instrument. So from my world, if we're putting a sensor in a satellite that's in Earth orbit, and that sensor is imaging the Earth's surface, it is a remote sensing instrument. So I mentioned that image of the Statue of Liberty. Well, this particular image was acquired from the WorldView 2 satellite, which is in Earth orbit about 480 miles above the Earth's surface. So that image was taken almost 500 miles away, truly remote when we talk about remote sensing. Now, the WorldView 2 satellite is owned by a company called Maxar. And the National Reconnaissance Office has a contract currently with Maxar to provide Maxar or images from Maxar satellites to the defense and military community and to civil agencies such as the USGS. So that's how I was able to acquire that image. Now that image was bought and paid for through that contract that the National Reconnaissance Office has. So I didn't have to, pay for that image out of my budget. It's already been bought and paid for. Kind of that concept of bulk buying, right? This image should only be bought once by the taxpayer. We shouldn't have the USGS buy it and the military buy it. No, we should just buy that image once. So it's a good deal for the taxpayer. So two types of remote sensing sensors. A passive sensor, and that image of the Statue of Liberty is an example of a passive sensor, where the WorldView 2 satellite in Earth orbit was picking up the sun's reflection, right? The sun was shining on the statue. It was reflecting back into space, and the WorldView 2 sensor picked up that image. So that's an example of a passive sensor. We also have active sensors where the sensor itself creates a pulse of energy that, in this case, goes from the satellite down to the Earth's surface, bounces back up, and is acquired or picked up by that same sensor. So radar is a good example of a passive sensor. So this is an example of a passive sensor. We have this area of the Aleutian Islands. I was given a talk a while back, and one of the USGS senior leaders was in the audience, and I actually had titled this "A Typical Weather Day in the Aleutians," and he kind of started laughing out loud, and he called out and says, "No, Paul, that's a good weather day." And so in this particular case, what we actually wanted to acquire was an image of volcanoes that were beneath that cloud, but that passive sensor, the sun was reflecting off the cloud, and that's what this sensor picked up. Whereas what we truly wanted was an image like this. This is an example of an active sensor, or taken from the TerraSAR X satellite that's operated by the German space, the German Space Agency folks. And the advantage of radar, it's able to penetrate clouds, it's able to penetrate ash and smoke, and you can see clearly those images of the volcanoes. And so my office is able then to better understand what is going on those volcanoes. Mitch mentioned that next month's public lecture is from a colleague of mine that will be speaking more about volcanoes. So think back to this talk. We work very closely with the Alaska Volcano Observatory and provide information to them. Okay, so another important type of remote sensing is infrared imaging. Now, this cannot be seen by the visible eye. It's actually more felt as heat, but within the earth sciences, it's very important to help us detect wildfires, to study the health of vegetation, to look for water and to study water, soil moisture, climatology, amongst other examples. So the two images here, the image on top is just a normal, what we would call a visible image, where it's that's just a passive image that the sun is reflecting off of the smoke. But the bottom image is an infrared image, and so you can clearly then see the areas of orange and yellow are where the fire is located. So that infrared image is picking up that heat. So just one more example, a little bit larger, perhaps easier to see, from a fire last fall. And again, in the center of that image, you're able to clearly see where that see right up here, that's where that fire is located. Okay, so just to wrap up my definition of remote sensing, within the earth sciences, there are many applications. I couldn't possibly capture them on a single slide. I just gave you some examples here, and you can read them as I go through. I also have a couple of images to show. Now, these images come from the Landsat satellite, which is operated by the USGS in partnership with our NASA partners. So this is an example, Imperial Valley, California. You can clearly see the agricultural area in bright green. This is an example in Nevada, so good to study the geology. In the image, this is Kilauea, volcano in Hawaii, and you can see the black there is the more recent volcano lava. And then finally, an image of Denver, Colorado, useful to study the growth of urban areas. So again, remote sensing is a vital tool within the earth sciences. Okay, the third question I'm going to answer is, so how did the U.S. Geological Survey, a civilian agency, come to partner with the military and intelligence community? So I'm actually going to start in 1869 with John Wesley Powell. Powell served as a soldier. He was a Union soldier during the Civil War. He lost part of his right arm in the Battle of Shiloh, and he served under General Ulysses S. Grant for part of the time that he was serving. After the war, he became a geology professor and began to explore the West. In 1869, he made plans to journey down the Green and Colorado rivers with a goal of traveling through the Grand Canyon. Now, he went to look for funds to help his trip. He did not receive or was not provided any funds from the government. It was all private funds. But he did go to his old commanding general and asked General Grant, is there anything you can do to help me in my trip? Grant said, look, I can't give you any money, but I can allow you to buy allow you to buy supplies off of Army contracts. So again, that would have been a huge cost savings to Powell, because the Army is going to be doing this bulk buying, and presumably they already would have had the supplies out west near Powell's trip. Now, I don't know if Powell ever took advantage of that, but he was offered that opportunity. So a good example of the military and the connection with the military benefiting, in this case, an earth science venture. So Powell continued to explore the West until 1881, when he became the second director of the USGS, and where he served for 13 years and was very influential in the early times of USGS. So a couple years after Powell started his exploration, Army Lieutenant George Wheeler was assigned the task to map the west of the 100th meridian, which is a line that goes from beginning in North Dakota down through Texas. So imagine that line, and he was tasked with mapping everything west of that. It was not well mapped, not well explored or understood. Now, Wheeler was trained as an engineer or a topographic engineer at West Point, and so that was his duties in the Army, was basically exploring and mapping. Now, the Wheeler survey and what became the Powell survey and two other great surveys of the West, Congress merged together in 1879 to form the USGS. And so Wheeler, while he didn't continue on and work for USGS, he continued his Army career. What he started to map the West and the processes and procedures that he developed came to USGS and formed the basis of our topographic mapping program. And I believe my colleague Mike Tischler gave a public lecture last fall, perhaps, on the successor, the National Geospatial Program. So again, that was Army knowledge, technology, expertise coming into civilian government. All right, one more example, and that's from World War I. So at the beginning of World War I, many of the USGS topographic engineers, as our cartographers were known at the time, joined the Army. World War I saw many technological advances, the use of airplanes for one, and the use of putting cameras in airplanes, flying those airplanes over the battlefield, taking images or photographs of the battlefield, and using those aerial photographs to create and updated maps of the battle. Now, after the war, those topographic engineers came back to their civilian agencies. There's one example is Claude Birdseye, who joined the Army as a captain, later promoted to a lieutenant colonel, and he eventually became, after the war, the chief topographic engineer of USGS. So they brought back to USGS and other civil agencies this knowledge and expertise developed during wartime, how to make maps from aerial photographs. And the whole science of what we now call photogrammetry was developed by these civilian agencies with expertise developed during the war. Okay, so let's jump up to 1960, where the story of my office kind of begins. So 1960, August of 1960 was the launch of Corona, the nation's first photo reconnaissance satellite. This was an absolute technical challenge. So to build a rocket, build a camera that could withstand a rocket launch, withstand outer space, operate that camera in space, turning it on and off when you wanted to take images, advance that film into a return capsule, return that capsule through Earth's atmosphere, capture the capsule midair. That's the photograph here is capturing the capsule in midair, and then bringing that film back down to Earth and processing it. So Corona saw many firsts. The first man-made object retrieved from space, the first mapping from space, and the first film taken from space. So, but it was a huge cost. It took 13 prior missions before they were able to successfully return film to Earth that could use. So a lot of cost went into that. Here's an example of a Corona image taken in 1969 of the San Francisco and Golden Gate Bay area. So you see the good quality that this was even back then in 1969. So because of that great cost and great investment the government was making, folks began to ask questions. The then Bureau of the Budget asked, gee, civilian agencies like USGS, can you use this newfangled ability to take images from space for your mapping? The answer was yes. President Johnson's science advisor established a committee that investigated the scientific uses of this photography. USGS had somebody on that committee. All this culminated in Congress appropriating USGS funds to build our own secure facility. Back then, the existence of Corona and this capability was highly classified. So we had to build a special secure facility in order to even use the Corona film. So we began to update and revise our topographic maps. Other federal agencies came in and started to use the film for their own missions within our facility. Now then 1974 happened, and the New York Times published an article with allegations that the intelligence community was spying on Americans. President Ford established a commission chaired by his vice president, Nelson Rockefeller, to look at those allegations. So 2 critical pages of that report, and I know this is too small for you to see, but Chapter 16, Domestic Activities of the Directorate of Science and Technology, Section 2, Overhead Photography of the United States, and then the relative pages 230 to 231. So in that report, they or on those pages, they actually said that yes, we have been the CIA, or Central Intelligence Agency in this case, that was operating Corona, was actually imaging domestic areas of the United States, but they were providing that film to civilian agencies to help those agencies meet their statutory missions. They particularly called out mapping, assessing natural disasters, oil spill tracking, helping to plan the Alaska pipeline route, and you see the others of forest inventory and determining snow cover. So that report also made a recommendation number 29, that a civilian committee should be reestablished. The earlier committee President Johnson established had been disbanded by this time. So the report recommended that a committee be established to provide the necessary oversight and coordination. Now, President Ford, that report went to President Ford. He provided answers to what recommendations he was going to take. And so there was a recommendation that he directed his National Security Advisor, Budget Director, and Central Intelligence Director to actually establish that committee. And they did so via a memo written October 3rd, 1975, directed to the Secretary of the Interior. Now, at first you may wonder why the Secretary of Interior. Well, it made sense. The USGS, we are a part of the Department of Interior. We had been up and operating our own secure facility. We had been using the Corona data. And in 1972, USGS was one of the agencies that helped launch the Landsat satellite, which began to image the land areas of the globe. So we had a remote sensing program in place. So just a mission, I'm not going to read this word by word, but essentially what we now call the Civil Applications Committee is one of the functions that my office provides the Secretariat for, and that committee is to provide the necessary oversight and facilitation of when federal civil agencies use the military and intelligence community's remote sensing capabilities. So that committee, as I mentioned, is up and running, chaired by the USGS director. The charter was the most recent charter signed by the Secretary of Interior and the Director of National Intelligence. So 12 civil agency members of the committee, the Departments of Interior, Agriculture, and Commerce, the first 3 there. Also the Federal Emergency Management Agency, and the next row, NASA, the National Science Foundation, Department of Transportation, the Coast Guard. Last row, Department of Health and Human Services, Environmental Protection Agency, the Army Corps of Engineers, and the Tennessee Valley Authority. So all and the Army Corps of Engineers for their domestic mission. We're also joined by 7 associate members. These are all members that are officially a part of the intelligence community, the National Reconnaissance Office, National Geospatial Intelligence Agency. We work with those 2 agencies very closely, Departments of Homeland Security, Defense Intelligence Agency, National Guard Bureau, Departments of State, and Energy. So also have 3 members that serve in an ex officio or a policy oversight role, the Office of the Director of National Intelligence, the President's Office of Science and Technology Policy, and a parallel committee to the Civil Applications Committee, and that's what's the National Committee on Geospatial Intelligence that oversees the same technologies by the military and intelligence community. So, okay, just a couple quick stories, quick benefits. I mentioned we started to revise and update topographic maps. We first started to work on the 1 to 250,000 scale. That is 1 inch on the map is 4 miles on the ground. We did a complete revision of those maps using the Corona data. And if you go down to the lower left-hand corner is a description of what data, what went into making that map. And I'll bring you down to this line here, preliminary revised by the USGS from aerial photography taken 1974 to 1976 and other data sources. Now, USGS is never vague about the data that we use for our maps or our scientific research. We're completely transparent in that realm, except back then the fact that we were using Corona was classified, so we couldn't share that we were using classified information, so we came up with this and other data sources. So this is what that data source looked like. This image has now been declassified, so it's from the Hexagon satellite, which was a successor to Corona, and that declassified film is now housed at the Earth Resources and Observations Science Center in Eros, or also called Eros in Sioux Falls, South Dakota, and it's available via our Earth Explorer website. So just another quick benefit, this is a 1 to 24,000 scale topographic map, or 1 inch on the map is 2,000 feet on the ground. The accompanying hexagon image that was used to update that topographic map, and then the revised topographic map. And again, down in the lower corner is the description of the data, and you see it, you know, we had to be vague and say this other sources were used. We also used the Corona and hexagon to help us determine what parts of the country we needed to revise, so we could quickly look at the film, evaluate the film versus the topographic maps, and determine what areas to revise or what areas we needed to fly aerial photography. Okay, so the crux of my presentation, I just have a whole series of applications just to give you a flavor for the type of work that we do. So, you know, we do, in my office in particular, we monitor volcanoes across the globe. We work with our earthquake scientists and support their needs. We do wildfire detection and mapping. We've worked with our landslide program. We look and support studies on flooding and hurricane relief. We help with land, water, resource management, environmental monitoring, and finally mapping. So the volcanoes, so we monitor volcanoes not only for the local population that might live on that volcano, but also for aviation safety. As it turns out, a lot of volcanoes are along the Aleutian Island chain that happens to coincide with the normal air route between North America and Asia. And so it's very critical that we keep those plains away from any ash clouds that might be generated by the volcanoes. And so we support the USGS Volcano Hazards Program and its observatories. The image map on the right is one that my office created. We took the base image is again an image from Maxar that we updated after the volcanic eruption. This is a Boguslav volcano, erupted in December of 2016, and we provided this update and provided to our USGS colleagues that operate the volcano, the Alaska Volcano Observatory, and they posted it on their public website. We also worked in 2018 with our colleagues at the Hawaii Volcano Observatory during the Kilauea eruption. We were tracking the lava flows. You see an example here on the right. And the key thing was to help keep the local population safe from the lava flow. So my office was providing information to our colleagues in Hawaii that were combining what we took or what we were creating with observations and other data that they had, and then daily we're posting the updated maps like you see an example there. So just I couldn't help but put in one more volcano image. So this was a volcano that erupted in January in the Kingdom of Tonga. This is a before and after image, and you see this was a huge eruption that took place. So images like this help volcano scientists understand the eruption, but also, as you'll see examples later on, this type of imagery also helps with areas that are impacted by disasters and help with disaster response. An important mission that my office supports is wildfire detection and mapping. We work wildfire detection with a large number of partners, and together we feed information to the National Interagency Fire Center, who then further disseminates the wildfire detections out to local responders who are able to respond to the fire detections. My office also provides a bit of a surge mapping capability. We're available to help when there's a large number of fires, and our other partners are maxed out. We're able to help and provide wildfire response maps like you see on the slide here that has an outline of a wildfire and hotspots detections. So we also have worked with the USGS Landslide Hazards Program after Hurricane Maria devastated Puerto Rico in September 2017. The landslide folks wanted to document where in the islands that was impacted by landslides. So we were able to acquire digital globe imagery for the entire island. You see an example here from their report where they documented the homes that were destroyed and also the roads that were blocked. This is important information to in this case, the Puerto Rico government. They're able to ascertain the amount of damage and the roads that are blocked, help in response, and get help out to their population. An example from a hurricane, this was the impact of Hurricane Ida that devastated, began in Louisiana, came up and drenched parts of New Jersey and New York. You see before and after images here. The upper two images are TD Bank Ballpark in Bridgewater, New Jersey, and the lower two images are Manville, New Jersey. Now, my office is responsible for tasking and acquiring imagery, in this case from Maxar, but we also work with the Earth Resources Observation and Science Center in Sioux Falls, who provide the data through their hazards data distribution system, and you see the website up there. So this is important to local and state government responders and others that are helping in disaster response and recovery. They're able to access this imagery as well. So oil spill monitoring example from our colleagues at the National Oceanic and Atmospheric Administration, an example of the digital globe imagery on the left and radar data on the right. They're able to use both kinds of imagery, again, a passive sensor and an active sensor, to help map and monitor oil spills. So just a couple of examples from the environmental and ecological studies. This is a project that we provided data to the Forest Service for helping them to track the southern pine beetle activity that can devastate large areas of forest. We've supported a number of folks, including USGS and again, the National Oceanic and Atmospheric Administration on doing various river habitat studies. And finally, the National Park Service, one of our sister bureaus in the Interior Department, who were determining vegetation cover and looking at bison areas and also looking at prairie dog town conditions. And then an example from the National Science Foundation, who were able to use Maxar data for the entire continent of Antarctica to provide an up-to-date terrain map. We had terrain maps. They weren't terribly accurate, but the National Science Foundation, in partnership with the Polar Geospatial Center at the University of Minnesota, were able to update this terrain map, which has been very beneficial for studies in Antarctica. And then a project that my office has been responsible for, the Global Fiducial Library. It's areas across the globe that we have been systematically collecting data for or of since the 1990s. We are able to derive and release publicly this data. This is an example from Fire Island National Seashore. There was Superstorm Sandy came through and punched that inlet, and then we are able to track through this imagery how that inlet grew over time. So just to end my presentation with a couple of international examples, my office also supports the International Charter for Space and Major Disasters, where countries across the world who have remote sensing capabilities and commercial companies as well agree to provide that data at no charge to a country that's experiencing any type of a disaster. So again, that data are made available through the Hazards Data Distribution System, and my office provides the data tasking. This is an example of in South Africa, who experienced some terrible flooding and landslides, again, a before and after image, so you can track the damage. This is an example from Micronesia that experienced some severe coastal flooding that damaged a causeway that connected two of their more populated islands. And so you can see the damage to the causeway. Oops, gotta get my cursor right about there, is the damage to the causeway. And finally, another oil spill example. This is an interesting story. I showed you the image of the Tonga Volcano. Well, that volcanic eruption was so huge and large, it created tsunami waves that traveled all the way to South America. It rocked a ship, causing that ship to discharge oil, and that oil was in a pretty environmentally sensitive area. And so our friends at NOAA produced the oil spill map that you see there to help our friends in Peru track that oil. So that pretty much ends my presentation. I just wanted to end though with a word of thanks. You know, I've been in this job for 5.5 years, and I have just been very impressed by the partners and the folks that we work with in the military, Department of Defense, and intelligence community. You know, as you've learned in this briefing, we've been partnering with them for over 50 years, and these are dedicated professionals. They're there to help protect and defend our country. They do that very well, in my opinion, but they've also been a tremendous help to civil agencies such as USGS. And you know, I have a staff that has done all the work that I've been able to present here, and so just want to give a shout out to my staff for their dedicated work. And with that, I am going to turn it back over to Mitch, and happy to answer any questions that folks might have. If you have questions after this briefing ends, you can always feel free to mail me. Mitch, back over to you.
Okay, thank you, Paul. It was really interesting to see how much remote sensing data is used and how much is used and where it's used and how it's used. As a reminder, if you'd like to ask a question, remember to click on the Q&A chat window. Look for the question mark in the upper right-hand corner of your screen, and we can get to the questions. Let's see. First question is from John H. And he wants to know, do we have the same bulk buy arrangements with the Germans who got the Aleutian Islands image? And what about imagery from other countries?
Okay, all right, good question, John. Thanks for asking. So, so the German images were actually acquired from our relationship with the National Geospatial-Intelligence Agency, right? They're the agency that is responsible for mapping, providing maps to the military and intelligence community folks. So they have got partnerships with other countries who often share data with each other, and so the NGA, or the National Geospatial-Intelligence Agency, was using the TerraSAR-X data for a project that they were doing, and they were able to share. They had gotten permission to share some of that data with the USGS.
Okay. Can USGS CAC task NRO satellites to get imagery for disasters, e.g. earthquakes?
Yes, we do task and use NRO satellites in addition to the commercial examples that I showed here.
Okay. From Susan, wants to know, can you describe what you mean when you talk about the Civil Application Committee providing oversight?
Mm-hmm. Sure.
Do you have any examples?
Good. All right. Thank you. I tried to cram in a lot in 45 minutes, so I appreciate the questions, because that allows me to say some things that I had to kind of cut out. So, so because we are using remote sensing data that is procured, bought, and paid for, and appropriated from Congress to the Department of Defense, there are restrictions to using that data, right? We still have to, protect private liberties. We have to, protect how we use that data. We have to protect the use of that to make sure it's not misused, right? And so there's a number of executive orders, laws, and regulations that control and prohibit our use. So we can't image U.S. persons, for example. And so the Civil Applications Committee was then established to provide that necessary oversight. So oversight is always required when we're using these images, domestically or by domestic agencies. So hope that answers your question.
Okay, another question from John H. Approximately how much time elapses from when the military takes images of disaster situations? Can you make the images available to the civilian agencies that need them?
Yeah, so I'm going to answer that question in terms of the commercial vendors, because that's where we work with most closely for disasters, because that imagery can be made available, to state and local responders. And so we get that imagery pretty quickly. If there's an ongoing disaster and folks know that there are lives, in danger, I don't know if I can put an exact time on it, other than we can get it in the hands of responders. I'm going to say within an hour, but it's probably less than that. But that would be my best guess to put a time on to it.
Okay. Wants to know, do you have hyperspectral sensors at play also?
So there are a couple of countries, and there's a couple commercial vendors that are planning to launch hyperspectral. I actually just came from a conference a couple of weeks ago, and there was a number of vendors there sharing their plans to launch hyperspectral. And I think one or two other countries have it as well, although we're not right now accessing it. So any of the hyperspectral that we get is typically collected from an airplane or a sensor in an airplane that's readily available to us, or in an unmanned aerial system as well. Many of our scientists will use hyperspectral collected from those two platforms.
Okay. Do we have links to other agencies for observations of the moon and other planets?
Well, maybe a future public lecture from our astrogeology program, folks. Have you?
Yeah, I would say talk to them about that one.
Yeah, that's we have an astrogeology office in Flagstaff, Arizona. They're doing Moon and Mars imaging.
Okay. And a question from Alec. He says, how much of the total historical mapping projects of USGS reside only on paper and not in any digital GIS formats?
Okay. Good question. I don't have a, what I would suggest is that was a question that Mike Tischler may have answered when he did his public lecture. And Mitch, you may remember, or Amelia, that was last fall sometime. So I'm not going to answer that because I don't want to be wrong, but I do know they have scanned many maps, but I don't know how many, or I won't say all because I don't want to be wrong, but I think Mike answered that question back in his public lecture.
More and more of it is made available digitally. It may be, like PDFs or TIFFs and not necessarily GIS format.
Yeah, they try to do what's called a either GeoTIFF or GeoPDF, because we do recognize that many folks want to put it into a geographic information system. What I would suggest is visit the National Map website, and if they're for historical maps, that's where they're made available.
Right. Second part of the question is how much USGS historical mapping materials has been degraded by time or even lost?
Oh, that's kind of outside of my program purview to answer. We've got the USGS library, which would have a complete collection, and I know they take good care of all of their documents, but I'm not really in a place to answer that one.
Yeah, I know that Aeros Data Center is working on scanning a lot of the historical aerial photos because there is an image, there is a problem with the degradation of the photo negatives.
Sure. So I mentioned that I had some examples of some of the Corona and Hexagon. When that film is declassified, a copy of the film was sent to Aeros in Sioux Falls. So they were actually working to get all of that film a high resolution scan. Right now it's scanned on demand. So if a customer wants part of the film scanned that hasn't been scanned, there's a one-time $30 charge. that high resolution scan is made, and then it's made available to whoever pays for it, and then it's added to the collection that is publicly available. I know that's the case for the declassified film, and there are efforts underway. There's a lot more film that we expect to be declassified, and there's certainly an interest to get that scanned before the film degrades.
Okay. What are the next challenges and new technology developments in remote sensing?
Oh, wow, what a cool question. Well, the question about hyperspectral came up, and once we get a couple of companies, right now there's a number of companies that have satellites in orbit, right? And so, and actually just yesterday, I mentioned the National Reconnaissance Office is the office that contracts with the commercial companies. So actually just yesterday, they announced 3 new contracts. The current contract that we get the Maxar data from is going to be expiring shortly. And 3 new contracts have been put in place with Maxar, Planet, and Black Sky, three different companies. Planet is their goal is to image the Earth every day. And so I think the challenge is, now that I've had some time to think about it, is there is so much imagery that's being generated, we can't put our human eyes onto it. And so there's lots of effort at what we call artificial intelligence. So, can a computer look, quote unquote, at an image and pick things out? So, in the examples that I showed of a before and after, the landslide, for example, or the flood, could a computer counted the houses that have been flooded? Or could a computer showed you the streets and roads that are blocked without a human interpreting that? That would be a tremendous benefit, and to do that quickly, right? Because huge areas might be flooded during a hurricane. Well, it takes right now humans a lot of time to look through all that imagery. So this whole idea of artificial intelligence or machine learning is really the next big goal of remote sensing. So great question.
Yes, it was. John H. wants to know, will these slides be made available in some form on the web, either for download or simply to consume as web pages?
I think you all recorded this, right? Or are recording this, so the recording will be available.
Yeah, the video will be up in about a week.
Okay.
Okay, question from Chris. Wants to know, can you estimate the value of federal dollars saved by leveraging the NRO contracts to buy once and use many times?
Oh, I wish I could, man. That's a question. I've talked to some colleagues who are economists, and I said, can you answer this question for me? So no is my honest answer. But I really wish that I could, because I think that's a very valuable, that would be a very valuable number to have. So, I can tell you, I mentioned the contracts that the NRO announced yesterday, and 2 of the companies have come out with, how big that value of the contracts are. And I think one was like $3.5 billion, and the other was, I don't remember the exact number, between $1 to $2 billion. So, what I tell folks is, look, my office is able to task these multi-billion-dollar contracts, but that's not the same. That's not the answer to the question. But I sure wish I could.
Okay, last question. It looks like Bill K wants to know, have you ever used satellite images taken at night on a project, maybe fire mapping?
So that's where radar comes in. You know, I showed the example of radar being able to penetrate a cloud. And so that's where radar doesn't need the sunlight, so it can operate, and it does. We do, you know, we're able to task the radar to collect a day or a night.
Okay, I think that's all the questions we have time for this evening. It's also all the questions we received.
Okay.
So I would like to thank you again, Paul, for your talk
Okay.
today and answering all those great questions. And again, thank all of you who came out and joined us today. In case you would like to watch this again or share it with others, Paul's lecture will be available in about a week for on-demand viewing at our website at www.usgs.gov/PLS. We also find around 180 archived public lectures on that site, spanning over 20 years of public lectures like this. So be sure to check it out. On the website, you will also find our lecture schedule for the remainder of 2022. Coming up this year, we have talks on topics ranging from geologic mapping to endangered bumblebees. If you would like to be added to our mailing list, you receive notices. To receive notices about our public lectures, just send us an email at wmcesic@usgs.gov, and we'll add you to the list. Finally, we hope you will join us again next month on June 30th at 6 p.m. Pacific time for Michelle Coombs' talk on Alaska volcanoes. Until then, thank you again for joining us and have a good evening. Bye for now.